Alright, yeah, welcome back again. So we are looking at a hyperparameter tuning in Python, and we want to consider the common two types of hyperparameter, which is a grid search and a randomized search. Okay, hyperparameter tuning is actually a process of finding the best set of parameters for a model to improve its performance. Okay, these are the settings we define before training a machine learning model. They are not learned from the data during training. So like model parameters like weight in linear regression or neural networks. So we have some examples of parameters such as linear rate in gradient-based model. We have number of trees in random forest. We have maximum depth in decision tree. We have number of hidden layers in neural networks. We have batch size, epochs, and in deep learning, and so on. So there are several examples like that, and we also there are basically many type of parameter tuning, many types, but we want to look at two types here: grid search, which tries all combination from a predefined list, simple but can be very slow. But we also have random search, which tries random combinations, often faster than grid search. So we want to see how do we implement this quickly and see the difference between the two. Right. So I'm going to implement it by demonstrating it using a parameter, using the breast cancer we consider data set. So we're going to load the data set. We have used it before. We load the data set here. All right. We load it here. We can see that we also standardize it here. Okay. We call our standard scalar. All right. So which is here. So we now standardize to make it to standardize. Then we print out a sample here. So this is our shape. We have 455 rows and 30 columns. So features now. So these are the features. Sample can see feature here. So we have a mean radius, mean texture, mean parameter. So these are just sample of what we have in our columns. All right. So let's look at defining the model now. So we define the model and parameter space first. We use a support for machine to demonstrate this. All right. So just from SQL, we import our SVC. Now this is just if so pass our 42 states random to it. Then we build our parameter grid. We build it here by passing our parameters. We have our C between 0.1, 110, and 100. You can add more to this to see how it works. So this regularization parameter. We have passed our gamma here, scale, auto 0.1, 1. These are kernel coefficients. We also pass our kernel type here, linear, RBF, and polynomial. So we polynomial actually have a degree, so which we render degree here 2, 3, 4. So degree that is polynomial kernel. All right. So now we want to look at a grid search first. So from here that we have built our parameter here from using a support virtual machine function. So we can now start with our grid search first. Okay, so it's a grid search. We call it a grid search function after we have imported our grid search function from the library. So we pass our parameter estimator, parameter grid, which we have built here. Don't forget, parameter grid is one that we built up here. Okay, we have built it up here, so we just pass it in. That is from the support vector machine. Pass it in. So we are trying to look at a cross validation 5. So you can increase to 10 later. So number of job 1, scoring, we are looking at accuracy. Verbose, our verbose is 1. So we execute this by starting a time so that we want to know how long does it take to process. So we start a time, call it time function. Don't forget, this is our import our time here, so that you can see the difference between the time process of the two. So we passing time to it to train. So we now call our function here. You can see the result here, what we have here. So for this parameter, so 15 folds for each of 144 candidates, totaling 720 feet. So grid search result, we have best parameter C is equal to 1, degree is equal to 2, gamma is equal to scale, kernel is equal to RBF. So RBF is what gives us the best here. So and our best validation is score is 0.99758, and our test accuracy is 0.9825. So the time it takes is 10.16 seconds. Okay, total combination tries 144. All right, so now for grid search, actually, we have a discrete evenly spaced value. Our example is C, which is 0.1, 1, 10, and 2. So, okay, for randomized search, we want to look at we just import our randomized function from from the library. So the parameter is now modified here. Okay, so you can see here we pass our log uniform here. You have this one. So exponential here. So logarithm distribution. So gamma rays here. Our kernel is using the same here, but with linear here. Degree. So you can see. So that is a parameter for that. So we set up the randomized search here, and we pass a parameter into it. We just use the same 5 consolidation, job 1, scoring accuracy, and those variables still 1. So we set our time as well to see how long it takes to process. So we see that the result here fitting 5 foot for each of the two. Our result here is showing here. If you have our result showing here, so you can see from here. So here we have fitting 5 foot elevation to 20 candidates, totaling 100 feet. Then we have base parameter C was 2.75, degree 4, gamma 0.1, kernel is it's also RBF. Our best consolidation is 0.9780. Our test accuracy is 98.25, which is similar. Then the time it takes to process is 0.5 seconds. 0.65 seconds. So now parameter space design for so you can use statistical distribution. Example, this is a log uniform for exponential sample logarithm, so more efficient for continuous parameters actually. So let's like comparison. How do we compare the two together? So we create a comparative table and plot it and plot the figure and see how it looks like. So we just pass our method, both grid search and randomized search here. We see our best accuracy, our test result, the time, and the combination tries. So from here, so we pass it in and we print our comparison method here, plot the figure here. So we can see here the result showing here the method, each method, and the best parameter accuracy we have is similar here. Okay, similar accuracy 97, 58, 97, 80. So randomized have a little bit more than this one. So just a little bit. Then we have a test accuracy here 98.24. This test accuracy is the same. So this one used 10.16 seconds, but this one used 0.65 seconds. So this is very fast. I mean that's randomized. So the first one tries 144, which is grid search, take a lot of time, while the second one use 20 try, which is very short time, and very short try, but the time is also short as well. All right, so you can see the table here, search time comparison, grid search, randomized search. You can see the time per second here. Grid search take a lot of time, while randomized take a short time. From I can see from here. Okay, so grid search have higher accuracy but longer time because it tries all 144 combinations. Randomized search slightly lower accuracy but much faster because it only 20 combinations. All right, so the key difference is here that when you are dealing with the both of them, you have to look at the features. Okay, now search strategy exhaustive all combinations for grid search, random sampling of parameters, randomized. So that one is randomized. So we have parameter space, okay, fixed discrete values. This one can handle distribution, e.g. log uniform, that is exponential, and the combination computation costs high, grow exponentially for grid search, but for randomized are controlled by NTL, a number of iterations. That's what I mean. So we have our best for small parameters space, which is less than 20 combinations, large parameter space for randomized search. But for optimality, guarantee best in grid, but probabilistic in best in a randomized search. So now practical recommendation: when to use grid search now when you have fewer parameters, less than 5. limited possible values per parameters. It needs the exact best combination in the defined space. So we want to use randomized with many parameters, continuous parameters range, limited computation resources, quick initial exploration. So you can also use hybrid, which we first randomize to narrow down the ranges, then we apply grid search on promising regions. So in summary, we can say that a randomized search is 7 times faster in this example. Okay, difference grows exponentially with parameter space size, but in performance, grid search found slightly better parameters. Okay, better. So randomized search achieve comparable results with less computation. So in practical choice for production, we can start with a randomized search. Then for competition, one can consider grid search after narrowing down parameters. So it's just the difference between grid search and randomized search. So there's no actually best depend on the what you're working at, but grid search seems to have if you have a lot of time to spend, grid search is the best because it gives you a good result in that area. So, but if you know no time, you can just use randomized search quickly, and I think that should do well. So, thank you so much for listening. I will see us in the next class. Maybe looking at something more important or other areas of parameter tuning, which is a little bit more advanced than grid search and random search. Thank you so much. I will see you in the next class. Bye for now.